Welcome back. This is part 2, which is very short. So I just recall the definition of the model and I introduce the representation in terms of phases or angles. Okay, so these are definitions that you already know. So this is our d-dimensional hypercubic lattice. Sites are denoted like this. This is a set of bonds. They are pairs of neighboring sites where we use periodic boundary condition. The spin is a two-component vector with length 1, and this is spin configuration. This is our Hamiltonian. This is S dot S, Heisenberg ferromagnetic interaction, and the magnetic field in the x direction. And this is a partition function. This is the expectation value. And here ds denotes the integration over all possible spins, values of spins. Okay, since we have this kind of spin, planar spin, I think you can imagine that it is useful to introduce the angle in this way. So this is a picture, and then you easily find that this kind of inner product is written as a cosine of the difference in angles. So this denotes a collection of all these angles. So we use this instead of spin configuration. Okay, and then this is the Hamiltonian. Well, I think it's trivial. Here you have this S dot S, so it's written like this. And here you have S x component of spin, and x component is cosine. Okay, so this is our Hamiltonian, and this is partition function. This is the expectation value, and here this d theta simply denotes the integration over all this angle from 0 to 2 pi. And of course, this is exactly the same as this thing, and it is much more convenient to use this theta representation. So we are going to use this theta language throughout this mini course. And finally, you have this kind of useful, you can derive this kind of useful expressions. So what is this? First of all, I note that this Hamiltonian is invariant if you switch the sign of all theta. Okay. Well, it's just clear if you put minus here, minus, since cosine is an even function, nothing changes. In the original spin language, this is a symmetry with respect to this change. So you change the sign of sy, y component. Okay, anyway, we have this symmetry. Then let's look at, so we are interested in this kind of expectation value. This is expectation value of spin, the x component of a spin. And then this is of course this. Now, since we know from this symmetry that the expectation value of sine is 0 because of this symmetry, yes. And then you can just add to this plus I of this, and then this becomes this. So e to the I, the expectation value of e to the I theta. And of course, it's not quite natural to discuss this kind of complex quantity here, but theoretically, this is much more useful. Okay, and similarly, this is this, but you can add this, which is 0, and to rewrite this in this way. Okay, so in the rest of this mini course, I'm going to use these expressions, which turn out to be useful. Okay, so so this was really short part, so that's all. So good. So see you in the next part.